Hey there! Tonight, as the world outside quiets, we're going to embark on a gentle journey into one of the universe's most profound mysteries, the very nature of time itself. It's a concept we live with every second, yet seldom truly contemplate. Before we dive in, if you find yourself unwinding with these thoughts, consider taking a moment to like this video and subscribe to the channel. It helps us share these quiet explorations with more curious minds. From the steady tick of a clock to the tangled threads of memory, time feels both constant and elusive. We'll explore how it bends and flows, how it puzzles quantum physicists, and its role in the grand cosmic dance. But first, let's start with our own intimate connection to it. Consider your own heartbeat. A steady, rhythmic pulse, a fundamental internal clock that has been ticking since before you were born. It's one of our most primal experiences of duration, a built-in meter of existence. Then there's memory, a complex tapestry woven from moments. When we recall a distant summer day, time feels less like a straight line and more like a landscape we can revisit, some paths clearer than others. Think about how time seems to stretch when you're waiting, or how it races by when you're deeply engrossed in something you love. This subjective experience hints at time's surprising flexibility, even within our own minds. Our bodies are finely tuned to natural cycles, the circadian rhythm guiding our sleep and wakefulness, the lunar cycle influencing tides. These rhythms connect us to ancient patterns, long before we invented mechanical clocks. For our ancestors, time wasn't measured in seconds, but in the grand cycles of nature. The rising and setting of the sun, the phases of the moon, the changing seasons, these were the first, most reliable clocks. One of the earliest attempts to quantify time involved observing shadows. A simple stick in the ground became a gnomon, its moving shadow tracing the sun's path across the sky, marking the hours of the day. As the need for indoor or nighttime measurement grew, water clocks or clepsydras emerged. Water dripping steadily from one vessel to another provided a constant, albeit simple, measure of passing time. Beyond the sun, the stars and planets offered an even grander celestial clock. Ancient astronomers meticulously charted their movements, using these patterns to predict seasons, navigate, and organize their lives. These early sky watchers weren't just curious, they were practical. Understanding the precise timing of solstices and equinoxes was vital for agriculture, for religious ceremonies, and for the very survival of their communities. The rhythm of planting and harvesting, the timing of festivals, the organization of labor all depended on a shared understanding of when things would happen. Time became a social construct, a way to coordinate human activity. From these observations, units of time began to emerge: the day, the month, the year. These weren't arbitrary divisions, but reflections of the natural cycles that governed existence. Yet, even with these early clocks, the concept of now remained elusive. Is it a fleeting instant, a boundary between past and future, or something more fundamental, a continuously unfolding present? The Greek philosopher Heraclitus famously declared that you cannot step into the same river twice. This idea captures time's ceaseless flow, a relentless current carrying everything forward, never to return. Centuries later, St. Augustine pondered whether time truly existed outside of our minds. He suggested that the past is memory, the future is expectation, and the present is merely a fleeting transition. This raises a profound question. Is time an objective reality or a framework our consciousness imposes to make sense of change? The very act of measuring time implies its existence, yet its nature remains a riddle. If there were no minds to perceive it, would time still flow? This philosophical debate underscores the deep connection between our perception and the reality we inhabit, a question that continues to intrigue scientists and thinkers. For centuries, the accuracy of timekeeping was limited, but as scientific inquiry blossomed, particularly in astronomy and navigation, the need for precise, standardized time became paramount. It was Galileo Galilei, observing a swinging lamp in a cathedral, who noticed a crucial property. A pendulum's swing takes roughly the same amount of time, regardless of its amplitude. This isochronism was a breakthrough. Building on Galileo's insight, Christian Huygens designed and built the first successful pendulum clock in the 17th century. This invention was revolutionary, offering unprecedented accuracy in time measurement. Suddenly, time could be measured with astonishing precision, not just in hours, but in minutes and seconds. This wasn't just a technological marvel, it fundamentally changed how science was conducted and how society functioned. The pendulum clock provided a uniform, objective standard. Time was no longer just the sun's journey or the river's flow. It became a measurable, divisible quantity, a universal constant ticking away independently of human perception. Yet, even with this newfound precision, the deeper questions remained. What is this time that we so carefully measure? In our next chapter, we'll see how Einstein shattered this seemingly constant tick, revealing a universe where time is far more fluid and interconnected than we ever imagined. Until then, rest well. The precision of the pendulum clock, a marvel of the 17th century, solidified a compelling idea. Time was not just a fleeting sensation, but a measurable, uniform quantity. It seemed to tick on, independently of human perception, a silent, relentless beat across the universe. This notion gained immense traction in the Age of Enlightenment, a period brimming with new scientific thought and a fervent desire to understand the natural world through reason and observation. It was a time when the universe began to feel like a grand, intricate machine. At the heart of this era stood Isaac Newton, whose monumental work in physics and mathematics would shape scientific understanding for centuries. He sought to describe the universe with elegant, universal laws, and time was a critical component of his grand design. Newton famously articulated his concept of absolute, true, and mathematical time. For him, time flowed uniformly, without relation to anything external. It was a constant, universal river, always moving forward at the same steady pace everywhere. This absolute time was distinct from our personal, subjective experiences where minutes might crawl or hours might vanish. It was an objective backdrop against which all events unfolded, immutable and unyielding. For Newton, time was not merely a construct of our minds or a measure of change. It was a fundamental, independent dimension of reality, existing whether we perceived it or not, a universal constant. He envisioned the universe as a grand stage, with absolute space and absolute time providing the fixed, unchanging coordinates for all motion and interaction. Every event, from a falling apple to an orbiting planet, played out against this constant, universal canvas. This perspective brought a profound sense of order and predictability to the universe. It offered a comforting philosophical ease, suggesting that even amidst chaos, there was an underlying, unwavering rhythm to existence. Newton's concept of absolute time became the bedrock of classical physics. It allowed for the development of precise mathematical models to describe the motion of objects, from projectiles to planets. His laws of motion and universal gravitation, built upon this steady flow of time, enabled scientists to predict phenomena with astonishing accuracy. The universe, it seemed, was a giant clockwork mechanism. This newfound ability to calculate and predict celestial movements like eclipses and planetary alignments was a testament to the power of Newton's framework. The heavens themselves seemed to obey the dictates of this absolute time. The impact extended beyond theory. The Industrial Revolution, with its synchronized factories and complex logistics, relied heavily on precise timekeeping. Absolute time provided the common standard needed to coordinate vast systems. Though formalized later, the very idea of standardized time zones, allowing for global coordination, implicitly rested on Newton's premise that a universal time existed, independent of local variations. Yet, even with such advancements, a critical challenge remained: how to accurately determine longitude at sea. A ship's position east or west depended directly on knowing the precise time difference between its location and a fixed point, like Greenwich. The problem was so pressing that in 1714, the British Parliament passed the Longitude Act, offering a substantial prize to anyone who could devise a practical method for finding longitude at sea. It spurred a new era of innovation in timekeeping. Into this challenge stepped John Harrison, a self-taught clockmaker from rural England. Unlike the academic astronomers, Harrison believed the answer lay not in the stars, but in a clock so precise it could withstand the rigors of a sea voyage. He spent decades, not years, perfecting his sea clocks or chronometers. These were marvels of engineering, designed to compensate for temperature changes, humidity, and the constant motion of a ship, all factors that plagued earlier timekeepers. His fourth chronometer, known as H4, was a triumph. It was a compact, highly accurate timepiece, a stark contrast to the massive pendulum clocks that graced land-based observatories. It was time, contained and carried. The successful sea trials of Harrison's chronometers were revolutionary. Sailors could now determine their longitude with unprecedented accuracy, transforming global navigation and trade. The world suddenly felt smaller and more predictable. This triumph of engineering seemed to confirm Newton's vision. If time could be measured with such exactitude, surely it must be an objective, universal constant, ticking away independently of any observer or event. The idea of time as a steady, external river flowing uniformly from past to future became deeply ingrained in scientific thought and everyday understanding. It was intuitive, comforting, and seemed to perfectly explain the world around us. This simplicity and elegance offered a robust framework for understanding the universe. It allowed for clear predictions, precise measurements, and a sense of absolute order in the cosmos. Yet, even as this Newtonian view solidified, subtle questions began to emerge, almost imperceptible at first. Whispers of anomalies, faint hints that perhaps this constant, universal tick wasn't quite as absolute as it seemed. The stage was set, the grand clock was ticking, but a curious mind might begin to wonder, what if the stage itself was not so static? What if the river of time could bend or even ripple? In our next chapter, we'll journey beyond this seemingly fixed framework, to a time when new observations and radical new ideas would challenge the very foundations of absolute time, revealing a universe where time is not just a backdrop, but an active, dynamic participant in the cosmic dance. Until then, drift gently. The Newtonian stage, with its fixed backdrop of absolute time, had served science well for centuries. It brought order and predictability. Yet, by the turn of the 20th century, subtle cracks began to appear in this seemingly perfect edifice, whispers of anomalies that classical physics struggled to explain. One persistent puzzle revolved around light itself. Scientists of the era believed light waves, like sound waves, must travel through a medium. They called this invisible, all-pervading substance the luminiferous ether, thought to fill all of space. If this ether existed, Earth's motion through it should create an ether wind, much like a boat moving through water experiences a current. Detecting this wind became a crucial experiment, a way to measure our planet's absolute motion through the cosmos. In the late 1880s, Albert Michelson and Edward Morley devised an ingenious experiment. They built an interferometer, a device designed to split a beam of light, send the two halves along different paths, and then recombine them. Any slight difference in travel time caused by an ether wind would create an interference pattern. They meticulously rotated their apparatus, expecting to see a shift in the interference pattern as Earth moved with and against the supposed ether wind. The experiment was precise, careful, and repeated many times over. But the results were astonishing. No matter how they oriented their equipment, no shift was detected. The ether wind, it seemed, did not exist. Light always traveled at the same speed, regardless of Earth's motion. This null result was a profound shock to the scientific community. It contradicted deeply held beliefs about how light behaved and how the universe was structured. Classical physics, with its absolute time and space, seemed unable to account for this stubborn fact. Amidst this growing scientific unease, a young, brilliant patent clerk named Albert Einstein pondered these inconsistencies not from within an established laboratory, but from the quiet solitude of his own mind. He chose a different path. Instead of trying to find the ether, Einstein asked a revolutionary question. What if the constancy of the speed of light was a fundamental principle of nature? What if it was always the same for every observer, no matter their motion? From this audacious premise, combined with another fundamental idea, the principle of relativity, which states that the laws of physics are the same for all observers in uniform motion, Einstein began to weave a new tapestry of reality. One of the most astonishing consequences of these two postulates was time dilation. Imagine a light clock where a pulse of light bounces between two mirrors. For an observer watching this clock move, the light has to travel a longer diagonal path. Since the speed of light is constant for everyone, the light pulse in the moving clock must take longer to complete its journey from the perspective of the stationary observer. This means the moving clock appears to tick more slowly. Time, it turned out, was not absolute. It was relative to an observer's motion. The faster an object moved, the slower time would pass for it, relative to a stationary observer. This wasn't just a theoretical curiosity. This time dilation has been experimentally verified countless times. Subatomic particles called muons, created in the upper atmosphere, reach the Earth's surface far more often than classical physics predicts, because their internal clocks slow down during their high-speed journey. Even atomic clocks flown on airplanes tick ever so slightly slower than identical clocks remaining on the ground. The difference is tiny but measurable, a direct confirmation of Einstein's radical idea. Another profound consequence of this new understanding was the relativity of simultaneity. Einstein showed that events that appear simultaneous to one observer might not be simultaneous to another observer in relative motion. Imagine two lightning bolts striking the front and back of a fast-moving train. For an observer standing exactly in the middle of the train, the flashes might appear to happen at the same instant. They are simultaneous. But for an observer standing on the ground, watching the train pass, the light from the front of the train would reach them sooner than the light from the back, because the train is moving towards the front flash and away from the back flash. For the ground observer, the events are not simultaneous. Now was no longer a universal, shared moment across the cosmos. It depended on your frame of reference. This shattered the Newtonian idea of a universal, objective present. Einstein's special theory of relativity, published in 1905, fundamentally redefined our understanding of time and space. They were not separate, independent entities, but intertwined aspects of a single, four-dimensional spacetime fabric. This gentle revolution, born from thought experiments and a stubborn adherence to fundamental principles, revealed a universe far more dynamic and interconnected than anyone had previously conceived. Time was no longer just a backdrop, it was a participant. The universe was no longer a rigid stage, but a flexible, responsive entity where measurements of duration and distance were not absolute, but shifted based on relative motion. It was a dizzying, yet elegant, new reality. The implications were vast, extending far beyond the realm of physics. It challenged our intuitive sense of reality, prompting us to rethink fundamental questions about existence and perception. Yet, even with special relativity, there was a piece missing. It described how time behaved for objects in uniform motion, but what about objects accelerating or experiencing gravity? Einstein himself knew this. He spent another decade grappling with gravity, leading to an even more profound revelation, that mass and energy could actually bend the very fabric of spacetime, further intertwining time with the cosmos. We'll explore this deeper bend in our next chapter. Until then, rest gently. The elegance of special relativity revealed time's fluidity when objects moved. But Einstein knew a deeper challenge awaited. How did gravity fit into this new, dynamic universe? Newton's gravity was a force, an invisible pull. Einstein sought something more profound. He pondered not just motion, but acceleration, the feeling of weight. This led him to a remarkable insight. Gravity wasn't a force pulling objects, but a warping of the very fabric of space and time itself. This was the genesis of general relativity, where space and time, once thought separate, became inextricably linked into a single, four-dimensional entity, space-time. It was the stage, but now the stage itself could bend. Imagine a stretched rubber sheet. Place a bowling ball in the middle and it creates a dip. Roll a marble nearby and it curves towards the bowling ball, not because it's pulled, but because the sheet itself is curved. In Einstein's view, planets orbit the sun not because the sun exerts a force, but because the sun's immense mass warps the spacetime around it. The planets are simply following the curves in this cosmic fabric. This curvature affects not only space, dictating paths, but also time. In regions of stronger gravity, time itself slows down. It's a phenomenon known as gravitational time dilation. While special relativity showed time's relationship to motion, general relativity revealed its deeper connection to mass and energy. Gravity, the most familiar of forces, was now a manifestation of time's malleability. For an observer far from a massive object, time appears to pass more quickly than for an observer closer to it. The stronger the gravitational field, the slower time's rhythm. Einstein's equations predicted this effect precisely. It meant that a clock on the top of a mountain would tick imperceptibly faster than an identical clock at sea level, simply due to the slightly weaker gravity. Verifying such tiny differences required extraordinary precision. Early experiments like the Pound-Rybka experiment in 1959 used gamma rays to detect minute shifts in frequency as they traveled up and down a tower. The energy of a photon is related to its frequency. If gravity affected time, it should also affect the frequency of light. A photon climbing out of a gravitational field would lose energy, appearing to redshift or slow its internal clock. The experiment successfully measured this minuscule change, providing one of the first direct confirmations that gravity indeed warped time. The predictions of general relativity were holding true. Decades later, with the advent of highly accurate atomic clocks, even more striking demonstrations became possible. In 1971, the Hayfel-Keating experiment flew atomic clocks around the world on commercial airliners. They found that the clocks on the planes, due to both their speed, special relativity, and their altitude, general relativity, did not match the clocks on the ground. The combined effect was tiny but measurable. These clocks, based on the incredibly stable oscillations of atoms, are so precise they would lose only about 1 second in millions of years. This precision was crucial for detecting time's subtle shifts. Perhaps the most compelling and certainly the most common, everyday example of gravitational time dilation is the Global Positioning System, or GPS. Without accounting for Einstein's theories, it simply wouldn't work. GPS satellites orbit Earth at high speeds, experiencing both special and general relativistic effects. Their clocks tick slower due to their speed, but faster due to the weaker gravity at their altitude. These two effects largely cancel each other out, but not entirely. The net effect is that clocks on GPS satellites gain about 38 microseconds per day relative to clocks on the ground. If these minute differences weren't precisely corrected for, a GPS receiver would accumulate errors of several kilometers per day. Your navigation would be useless. So time is not merely a constant, unwavering backdrop. It is a dynamic participant, bending and flowing with the presence of mass and energy, an active part of the cosmic dance. This understanding profoundly shifted our perception of reality. Time was no longer universal and absolute, but local and relative, sensitive to the very geometry of the universe. Einstein's general relativity wasn't just a theory of gravity, it was a theory of spacetime itself, revealing a universe far more interconnected and responsive than Newton could have ever imagined. From the subtle ticking differences between a clock on a mountain and one at sea, to the precise functioning of our everyday navigation, time's quiet malleability is woven into the very fabric of our existence. Yet what happens when this fabric is stretched to its absolute limit? What happens when gravity becomes so immense that time itself seems to grind to a halt? In the extreme environments of black holes, time's behavior becomes even more bizarre, leading us to the edge of our understanding. And beyond the cosmic scale, in the realm of the very small, quantum mechanics presents its own perplexing relationship with time, a mystery will gently unravel next. Until then, rest deeply. While gravity's immense embrace reshaped time on cosmic scales, an even more profound challenge to our understanding emerged from the realm of the incredibly small. As the 20th century unfolded, a new physics, quantum mechanics, began to paint a radically different picture of reality, one where time's familiar rhythm seemed to falter. Classical physics, with its predictable trajectories and definite moments, worked beautifully for the everyday world. But at the atomic and subatomic level, particles behaved in ways that defied intuition, refusing to conform to the neat, linear flow of time we had come to expect. Here, now wasn't a fixed point. Instead, the very act of observation seemed to influence reality, blurring the lines between what was definite and what remained a spectrum of possibilities. It was a universe of probabilities, not certainties. One of the most unsettling discoveries was the principle of quantum superposition. A particle, like an electron, could exist in multiple states simultaneously, spinning both clockwise and counterclockwise, or being in several places at once until it was measured. This led to the measurement problem: what exactly causes a superposition to collapse into a single, definite reality? Is it the act of measurement itself, the consciousness of an observer, or some other, yet undiscovered, quantum process? If a particle's state isn't determined until observation, then does now truly exist for that particle before we look? This question challenges our fundamental understanding of a definite present, suggesting time itself might be fuzzy at its core. Consider a thought experiment. A tiny quantum event determines the fate of something larger. Until that event is observed, the larger system also exists in a state of superposition, a blend of possibilities. This blurring of states, this uncertainty about when a definite reality emerges, makes time less of a flowing river and more of a turbulent, frothing current at the quantum scale. Cause and effect become less straightforward. Physicists began to explore equations that tried to describe the universe at its most fundamental level, where quantum mechanics and gravity might eventually merge. One such equation, developed by John Wheeler and Bryce DeWitt, offered a startling revelation. The Wheeler-DeWitt equation, when applied to the universe as a whole, suggested something profound. Time itself might disappear from the equation. At the very deepest, most fundamental level, the universe could be timeless. This doesn't mean time doesn't exist for us. Rather, it implies that time, as we experience it, might be an emergent property, something that arises from the interactions of matter and energy, rather than a fundamental dimension of reality. If the universe's core is timeless, how does change occur? How does our experience of past, present, and future manifest? These are questions that continue to puzzle theoretical physicists, pushing the boundaries of what we can conceive. Further compounding the mystery is quantum entanglement, a phenomenon Einstein famously called spooky action at a distance. When two particles become entangled, they become inextricably linked, regardless of the distance separating them. If you measure a property of one entangled particle, the other instantaneously assumes a correlated state, no matter how far apart they are. This seems to defy the cosmic speed limit of light, and with it, our linear understanding of cause and effect. This instantaneous connection challenges the very notion of time's arrow. If information can be shared without time delay, does it imply a deeper, non-local reality where our sequential understanding of events is merely an illusion? Experiments have repeatedly confirmed entanglement, demonstrating that these quantum connections are real. They force us to reconsider if time is truly a universal, independent progression, or if it's more flexible, more interconnected than we ever imagined. The quantum realm suggests a universe where time is not a mere backdrop, but an active, sometimes ambiguous participant in the unfolding of reality. It's less of a clock ticking uniformly and more of a complex, vibrating web. This profound shift from Newton's absolute time and even Einstein's bending spacetime to the fuzzy, uncertain, and potentially timeless quantum realm represents one of the deepest mysteries in modern physics. It forces us to ask, is time fundamental, or does it emerge from something even deeper? Is it an illusion, a construct of our consciousness, or an intrinsic property of the universe that simply behaves differently at different scales? The quest to unify quantum mechanics with general relativity to find a theory of everything is largely a quest to understand the true nature of time. It's the missing piece in our grand puzzle of the cosmos. Perhaps time is not a universal constant, but a local phenomenon, a property of specific systems, like a localized ripple on a vast, timeless ocean. The possibilities are as perplexing as they are intriguing. The experiments continue, pushing the boundaries of what can be observed, revealing more about these peculiar quantum effects. Each new piece of data adds to the intricate tapestry of our understanding. From the steady tick of our internal clocks to the bending of spacetime around black holes, and now to the fuzzy, elusive nature of time at the quantum level, our journey reveals a concept far more complex than we first imagined. The quantum realm, with its inherent uncertainties and non-local connections, challenges our very notions of causality and sequence. It whispers of a reality where time might not be the fundamental arrow we perceive. Yet, even with this quantum weirdness, time seems to flow in one direction for us from past to future. This relentless forward march, this arrow of time, is another profound mystery, deeply connected to the universe's ultimate fate and the enigma of entropy, which we will gently explore next. Until then, rest peacefully. The quantum realm, as we gently explored, whispers of a time that is fuzzy, uncertain, and perhaps even emergent. It challenges our intuitive sense of a steady, universal tick. This peculiar behavior at the smallest scales leads us to an even deeper question. Is time truly fundamental, or is it a grand illusion arising from something else entirely? The greatest challenge in modern physics lies in unifying Einstein's general relativity, which describes gravity and the large-scale universe, with quantum mechanics, which governs the subatomic world. Where these two pillars of physics meet, our understanding of time faces its most profound test. At the heart of this unification quest is the radical idea that time might not be a continuous, smoothly flowing river, but something discrete. Imagine not a stream, but a series of tiny, individual droplets, each a fundamental unit of time. This notion is explored in the realm of quantum gravity, a theoretical field attempting to describe gravity using the principles of quantum mechanics. It's here that the very fabric of spacetime is scrutinized at its most granular level. One prominent theory, loop quantum gravity, suggests that space itself is not smooth, but woven from an intricate, finite network of loops, tiny, indivisible atoms of space. And if space is quantized, perhaps time is too. Just as matter is made of atoms and space might be made of these space atoms, the idea emerges that time itself could be composed of fundamental, indivisible units, far smaller than anything we can currently perceive. These hypothetical time atoms, sometimes called chronons, would represent the smallest possible duration that has any physical meaning. Below this scale, the very concept of time might cease to exist. The smallest theoretical unit of time is known as Planck time, an unimaginably tiny interval, approximately 1043 seconds. It's the moment when our current laws of physics break down, where spacetime itself becomes a frothing quantum foam. If time is quantized, then there's a limit to how finely we can divide it. Events wouldn't unfold continuously, but as a series of distinct, instantaneous flashes. There would be a before and an after, but no true during at this most fundamental level. Our experience of continuous time, then, might be an illusion, much like a movie appears to be continuous motion, but is actually a rapid sequence of still frames. The flow we perceive would be an emergent property of countless tiny, discrete moments. This granular nature of time, combined with the inherent uncertainties of quantum mechanics, further complicates our understanding of causality. If events are not perfectly continuous, does cause always strictly precede effect in the way we assume? Some interpretations of quantum mechanics even hint at retrocausality, where future events might, in a subtle way, influence past ones. This is a deeply counterintuitive concept, challenging the very arrow of time. Experiments are designed to probe these limits, pushing the boundaries of what we understand about cause and effect at the quantum scale. Each new observation provides a piece of this complex puzzle. If time is truly emergent or granular, then what does now mean? Is it a universal moment, or is our present a localized experience, a product of our specific interactions within the quantum foam? The Wheeler-DeWitt equation, which combines quantum mechanics and general relativity, famously suggests that time might disappear from the fundamental equations of the universe. This implies a deeper, timeless reality beneath our temporal experience. This leads to the concept of emergent time. Time, in this view, wouldn't be a pre-existing dimension, but rather a property that arises from the changes and interactions between matter and energy. It's like temperature emerging from the collective motion of atoms. Our very perception of time's direction, the relentless march from past to future, might be linked to this emergence, perhaps deeply connected to the universe's increasing disorder, a concept known as entropy. Some theories even propose that time is intimately related to information. Perhaps the flow of time is a measure of the universe processing information, or the irreversible change in information states. Ideas like the holographic principle, where our 3D reality might be a projection from a lower dimensional boundary, also hint at time's non-fundamental nature, suggesting it could be a feature of this emergent projection. The extreme environments of black holes, where gravity is immense and time seems to halt at the event horizon, are crucial testbeds for these ideas. Here, the interplay between quantum mechanics and gravity becomes most apparent and most confounding. At the Planck scale, the very idea of a ticking clock loses all meaning. The smooth, predictable flow we experience breaks down into a chaotic, frothing quantum foam, where time, as we know it, simply might not exist. These scientific explorations inevitably lead to profound philosophical questions. Is time an intrinsic property of the cosmos or a construct of our consciousness? Is existence fundamentally timeless, with our experience of duration merely a localized phenomenon? The quest for a theory of quantum gravity is ongoing. There are no definitive answers yet, only intriguing possibilities that push the boundaries of human comprehension. Each theoretical model, each experiment, adds another piece to this grand, cosmic puzzle. Our lived experience of time, with its steady progression, is undeniable. Yet, at the universe's deepest, most fundamental level, time might be a macroscopic illusion, a beautiful symphony played by countless tiny, timeless interactions. Despite these quantum ambiguities, time still seems to flow in one undeniable direction for us, from past to future. This persistent arrow of time is another deep mystery, one intimately tied to the universe's tendency towards increasing disorder, a concept we will gently explore next as we delve into the enigma of entropy. Until then, drift gently. Even amidst the quantum weirdness, our experience of time remains stubbornly linear. We remember yesterday, but not tomorrow. This fundamental asymmetry, this relentless arrow of time, is one of the universe's most profound enigmas, a question that has puzzled thinkers for centuries. Why do dropped teacups shatter but never spontaneously reassemble? Why does cream mix into coffee but never unmix? These everyday observations reveal a deep, one-way street in the universe, a directionality that seems intrinsically linked to time itself. The scientific journey into this mystery truly began in the 19th century, as physicists grappled with the behavior of heat and energy. They observed that energy tends to spread out, to become less concentrated, less useful. The first law of thermodynamics stated that energy cannot be created or destroyed, only transformed. A powerful insight, yet it didn't explain why certain transformations always went in one direction. It was the second law of thermodynamics that provided the crucial clue. This law, in its simplest form, states that in any isolated system, disorder or entropy always tends to increase over time. Entropy is a measure of the number of ways a system can be arranged. A highly ordered system, like a perfectly stacked deck of cards, has low entropy. A shuffled deck with its many possible arrangements has high entropy. The universe, it seemed, was constantly moving from states of order to states of disorder. This inexorable march towards increasing entropy provided a compelling physical basis for the direction of time. It was Rudolf Clausius in the mid-19th century who coined the term entropy, recognizing its fundamental role in defining the direction of natural processes. His work laid the groundwork for understanding this deep connection. Later, Ludwig Boltzmann offered a profound statistical interpretation. He showed that entropy wasn't just about disorder, but about probability. Disordered states are simply far more probable than ordered ones. Imagine a gas confined to one corner of a room. There's only one way for all the molecules to be in that corner, but there are countless ways for them to be spread evenly throughout the room, so they spread out. Time then flows in the direction of increasing probability. The past is low entropy, ordered. The future is high entropy, disordered. This statistical preference creates the arrow of time we experience. This explains why we can remember the past. It's a unique, low-entropy state that has unfolded into many possible future states. We cannot remember the future because it hasn't yet settled into a definite, low-entropy configuration. If the universe itself is an isolated system, then the second law of thermodynamics implies that the cosmos, too, is relentlessly marching towards a state of maximum entropy, a state of ultimate, uniform disorder. This ultimate state is often called the heat death of the universe, where all energy is evenly distributed and no further work can be done, no processes can occur. Time, in a sense, would lose its meaning. But here lies a profound puzzle. If entropy always increases, why did the universe begin in such an incredibly low entropy, highly ordered state? The Big Bang, the very beginning, was a state of immense order and concentrated energy. This initial low entropy was crucial. Without it, there would be no arrow of time, no flow for stars to form, for galaxies to coalesce, for life to emerge. It was the fundamental condition for our existence. Why the universe began in such a peculiar, highly improbable state remains one of cosmology's deepest questions. Some theories suggest it's just a statistical fluctuation. Others point to deeper, unknown physics. Inflation theory, which explains the universe's incredible uniformity, helps somewhat. It suggests a rapid expansion smoothed out early irregularities, but it doesn't fully explain the initial low entropy that drove the arrow. Even black holes, those cosmic devourers of order, play a role in entropy's march. While they seem to be ultimate orderers, Stephen Hawking showed they have an entropy proportional to their surface area. Through Hawking radiation, black holes slowly evaporate, radiating away their mass and energy. This process, though incredibly slow, contributes to the universe's overall increase in entropy, spreading out concentrated information. So, from the shattering of a teacup to the evaporation of a black hole, the universe is constantly, inexorably moving towards a state of greater disorder. This is time's unyielding arrow, etched into the very fabric of reality. This march towards entropy raises profound philosophical questions. Does meaning exist in a universe destined for ultimate decay? Or is our brief, ordered existence, our ability to create islands of temporary order, what truly matters? Perhaps our very consciousness, our ability to form memories and perceive a sequence of events, is tied to this entropic flow. We are observers caught within its current, defining our reality through its progression. The arrow of time, driven by entropy, explains why time flows in one direction. But the deeper mystery of the universe's initial low-entropy state, the ultimate source of this grand cosmic current, remains largely unresolved. This fundamental directionality, tied to disorder, shapes everything from the smallest chemical reaction to the fate of the universe. In our final chapters, we will journey into the extreme environments of black holes, where time bends to its limits, and consider how time plays out on the grandest cosmic stage. Until then, rest deeply. The arrow of time, driven by entropy, explains why our universe marches relentlessly forward. But what happens when this arrow encounters the most extreme conditions imaginable, where gravity warps reality to its very limits? Our journey now takes us to black holes, cosmic abysses where time itself takes a profound bow. These enigmatic objects, once mere theoretical predictions, are regions where gravity is so intense that nothing, not even light, can escape. They are the ultimate laboratories for exploring the boundaries of Einstein's general relativity, and with it, the nature of time. The idea of such extreme objects emerged from the equations of general relativity itself, first hinted at in the early 20th century. Scientists pondered scenarios where immense mass could collapse into an infinitely dense point, creating a gravitational well from which there was no return. As we've explored, Einstein showed that mass and energy curve the fabric of spacetime. A black hole represents the most extreme curvature possible, a deep, inescapable pit in this cosmic tapestry, and where spacetime bends, time itself must follow. Near a black hole, gravitational time dilation, a consequence of general relativity, becomes dramatically apparent. For an observer far away, clocks ticking closer to the black hole appear to slow down significantly, almost grinding to a halt. The boundary beyond which nothing can escape is called the event horizon. It's not a physical surface, but a point of no return. Crossing it means you are irrevocably committed to falling into the black hole's depths. From the perspective of an outside observer, someone falling towards a black hole would appear to slow down as they approach the event horizon. Their clock would tick slower and slower, their movements would freeze, and their light would redshift into oblivion. But for the person falling, nothing feels unusual as they cross the event horizon. Their own clock continues to tick normally. They wouldn't even notice the boundary, only the increasing pull of gravity ahead. This stark contrast highlights the profound relativity of time. There is no universal now or then near a black hole. Time's passage is entirely dependent on your position and motion within its immense gravitational field. Beyond the event horizon, the journey becomes even more bizarre. The gravitational pull on your feet would be vastly stronger than on your head, stretching anything falling in, a process vividly termed spaghettification. Within the black hole, the very fabric of spacetime warps so intensely that space and time effectively swap roles. The direction towards the singularity becomes inevitable, like time's arrow, and moving through time becomes like moving through space. At the very center lies the singularity, a point of infinite density where all known laws of physics break down. It is here that space and time, as we understand them, cease to exist. For the unfortunate traveler, the singularity represents the ultimate end. Time, for them, literally runs out, concluding their journey in a place where our most fundamental concepts of reality no longer apply. Yet black holes posed another profound challenge, the information paradox. If matter falls into a black hole, does the information it contains, every detail about its constituent particles, simply disappear forever? This question gained immense significance with the work of Stephen Hawking. He revolutionized our understanding of black holes, showing they weren't entirely black but had a subtle quantum glow. Hawking proposed that black holes emit a faint thermal radiation, now known as Hawking radiation. This radiation arises from quantum effects near the event horizon, slowly draining the black hole's energy over vast cosmic timescales. This means black holes are not eternal. Over unimaginable eons, they slowly evaporate, radiating away their mass until they eventually disappear completely. This process is incredibly slow for stellar mass black holes, but it has profound implications. Crucially, Hawking also showed that black holes have an entropy proportional to their surface area. This connected them directly to the universe's tendency towards increasing disorder, which we explored in our previous chapter. The paradox arose: if a black hole evaporates and disappears, what happens to the information of everything that fell into it? If it's truly gone, it violates a fundamental principle of quantum mechanics, which states that information can never be truly lost. Quantum mechanics dictates that the universe's evolution is always unitary, meaning information is conserved. If black holes destroy information, it suggests a fundamental flaw in our understanding of quantum reality. This information paradox has led to decades of intense debate and theoretical work. Some theories suggest information is encoded on the event horizon, others that it's subtly carried away by Hawking radiation in a scrambled form. Black holes, therefore, are not just cosmic monsters, they are crucial thought experiments, pushing our understanding of time, gravity, and quantum mechanics to their very breaking points. They force us to confront the limits of our current physics. They represent places where the familiar laws of physics, built on our experience of continuous time and predictable space, simply cease to apply. Here, time is not just bent, it is fundamentally reconfigured or even extinguished. The mysteries of black holes continue to challenge our deepest intuitions about reality. What truly happens at the singularity? Does information truly escape? These questions remain at the forefront of modern physics. From the relentless march of entropy to the time-warping depths of black holes, our journey has revealed time as a far more complex and dynamic entity than a simple ticking clock. In our final chapter, we will widen our gaze to the grand cosmic stage, exploring time's role in the universe's ultimate fate and its profound connection to our very existence. Until then, drift gently. Our journey through time has spanned from the tick of a personal heartbeat to the warped space-time around black holes. Now, as our exploration draws to a close, we cast our gaze to the grandest canvas of all, the universe itself and its cosmic clock. The very beginning of our universe, the Big Bang, wasn't just the start of matter and energy, it was the genesis of space-time and with it, time itself. Before this singular event, our current understanding of time simply ceases to apply. Imagine an infinitely hot, infinitely dense point. From this unimaginable state, roughly 13.8 billion years ago, the universe burst forth. This was the cosmic clock's initial tick, the moment duration began to unfold. We infer this beginning from echoes still present in the cosmos, like the cosmic microwave background radiation. This faint glow is the afterglow of the Big Bang, a snapshot of the universe in its infancy, only a few 100,000 years old. Since that initial moment, the universe has been continuously expanding. This expansion isn't just galaxies moving through space, it's the very fabric of space and time stretching, carrying galaxies along for the ride. The stretching of light from distant galaxies, known as redshift, confirms this expansion. The further away a galaxy, the faster it appears to recede, a direct measure of cosmic time's relentless progression. This cosmic expansion is our grandest clock, marking the passage of billions of years. Each second, each year, the universe grows larger, cooler, and less dense, forever moving away from its fiery beginning. But if time began with the Big Bang, will it also have an end? Cosmologists ponder various scenarios for the universe's ultimate destiny, each with profound implications for the fate of time. One dominant theory is the Big Freeze or heat death. This is the ultimate victory of entropy, where the universe continues to expand, cooling indefinitely until all energy is uniformly dispersed. In this scenario, stars burn out, black holes eventually evaporate, and matter decays. The universe becomes a vast, cold, dark expanse of scattered particles. Here, time would effectively lose its meaning, as no further change or process could occur. Another possibility is the Big Crunch, where the universe's expansion eventually reverses due to gravity. All matter would rush back together, collapsing into an infinitely dense singularity, mirroring the Big Bang. In a big crunch, time might appear to run backward, or at least lose its familiar arrow as entropy decreases. It's a speculative scenario, but one that challenges our linear perception of time's flow. Then there are cyclic universe theories where the cosmos undergoes an endless series of big bangs and big crunches. Time, in this view, would be an eternal loop, constantly renewing itself. More exotic scenarios include the Big Rip, driven by dark energy, where the universe expands so rapidly that galaxies, stars, planets, and even atoms are eventually torn apart. Here, time would simply cease to be relevant to any coherent structure. These cosmic destinies are not just theoretical curiosities. They are profound questions that force us to confront the ultimate nature of time, its beginning, its middle, and its potential end. Our journey has taken us from the intimate, subjective experience of time to its bending around massive stars, its fuzzy nature in the quantum realm, and its relentless march towards entropy. Time, it seems, is not a simple, unchanging backdrop. It is a dynamic, multifaceted entity woven into the very fabric of existence, manifesting differently across scales, from the smallest particle to the grandest galaxy. We have measured its flow with astonishing precision, seen it slow down, and even glimpsed hints of its disappearance at the most fundamental levels. Yet its deepest mystery endures. Is time a fundamental dimension or an emergent property of change? Is it an illusion or the very essence of reality? These questions continue to inspire and challenge us. Our personal experience of time, with its memories of yesterday and anticipation of tomorrow, anchors us. It is the narrative thread of our lives, shaping every moment, every decision. We are fleeting beings in a cosmic dance, our brief existence measured against billions of years. Yet it is within this finite span that we ponder infinity and seek to understand the very nature of time. The human curiosity that drives this quest, the patient observation, the flashes of insight, these are the hallmarks of our ongoing attempt to unravel the universe's most profound secrets. The scientific journey into time's mysteries continues, pushing the boundaries of what we know, revealing a cosmos far more wondrous and complex than we could ever have imagined. From the smallest quantum flicker to the grand sweep of cosmic evolution, time performs its endless, mysterious dance. It is the rhythm of existence, ever present, ever unfolding. And so, as the moon climbs high, casting its gentle light upon the quiet world, our journey through the enigma of time concludes. May its lingering mystery bring you a sense of calm and wonder. Sleep well.